Welcome to the first lecture of week 4, and in this lecture we will discuss supports and design of supports. So, let us start the discussion. Now, what is support to the vessel? Actually, whenever I am designing a pressure vessel, I cannot leave the pressure vessel as it is. It requires some structure or some assembly so that it can be connected to the foundation, and that assembly is basically called as support. So, design of vessel cannot be completed without selection and design of suitable support for it, and also without examining the effect of support on the shell. So, when I am connecting any support to the shell will put load on the shell will put load on the support, and in the similar line support will give reaction towards the shell. So, all these factors we have to consider for design of support. Now, if you remember the selection of vessel which we have discussed in the first lecture of this course, these are basically placed vertically or horizontally. So, as far as support is concerned, these are different for horizontal vessel as well as for vertical vessel. So, vessels such as distillation column, absorption column, evaporator and reactor, all these are placed in vertical position. However, horizontally placed vessels are heat exchangers, condensers. Heat exchangers can also be placed vertically and can also be placed horizontally. Now, we will see what are the supports used for vertical vessel and for horizontal vessel. So, for vertical vessel, we usually have 3 support. First is skirt support, second bracket or lug support, and third is leg support. So, skirt support is basically used for tall vessels like distillation column etc., which has height more than 20 meter. For that we use skirt support. Bracket or lug support are used for short height vessels, and similarly leg supports are also used for short height vessels. Okay. Now, for horizontal vessel we use saddle support as well as leg support. So, here we have different types of supports. In this particular course we will discuss one support for horizontal and one support for vertical. For vertical we will discuss bracket and lug support, and for horizontal we will discuss saddle support. So, let us start discussion on bracket or lug support, which is used to support the vertical vessel. So, here we have bracket and lug support. If you consider, this is basically the vessel, okay, which is denoted as A over here, and this particular assembly which is denoted as B, this particular assembly is called as bracket or lug, and this C part is basically called as column on which this bracket sits. So, bracket and lug supports are used to support vertical vessel of smaller height. Smaller height means which is subjected to minor wind loads. These can be easily fabricated from plates and attached to the vessel wall with a minimum welding length. Okay. Now, if you focus on this bracket or this bracket, it has 2 plates horizontally placed like this, and 2 plates vertically placed, and which we call as gusset plates. So, this horizontal and vertical plates are welded to the shell, and it creates a bracket. So, these are made on rest on short column. So, this C is basically the column which we have already discussed, or on beam of the structure depending on the elevation required. So, in this way we can understand the bracket or lug support, and then we will start design. But before we start design of bracket or lug support, we will see what are the stresses which are acting on these support. So, let us start that. The main loads on the bracket supports are dead weight of the vessel, which is its content, and wind load. So, as far as load is concerned on the support should be strong enough so that it can bear the dead load of the vessel, load due to its content and due to wind. Okay. Now, as far as dead load is concerned, what is that? which is basically which will always act. For example, if I am having the shell, for example, for a pressure vessel, the weight of shell will be there, weight of heads will be there, weight of attachment, for example plates are there and tubes are there inside the vessel. All these weight of all these assembly will be collectively added to dead load. Okay. And along with this we will consider another load which we call as load of content. So, load of content will also be bear by support. Okay. So, along with dead load we can have load due to wind. Now, if you focus on this particular figure, here this is the vertical vessel where bracket support is attached and wind pressure is coming from this side as it is shown over here. So, this is basically windward side, and here we have the leeward side where wind will try to turn. Now, as we have discussed that there are two loads, first is due to dead load and second is due to wind load. Okay. Now, once I am considering that dead load in this figure, all these dead load of the shell will try to put compressive stress in these columns, okay, or in the compressive stress to these support. And if wind is coming from this direction, it will also try to turn this vessel towards leeward side and put compressive stress to this way. Okay. So, once I am having leeward side, it means it has the maximum stress. However, when I am considering wind side or windward side, what happens? Due to load, compressive load will occur in a support, and because of wind it will try to turn it. So, wind will create a tensile load over here. Okay. So, load over here will be opposite to each other and which will be smaller than whatever is created in this way, because here both load are acting downward or acting in compressive way. So, as far as load is concerned, this would be the extreme condition for support to bear, and therefore, for design purpose also we will consider this condition where load due to wind and load due to dead load or dead weight will be considered together. So, let us start design of bracket or lug support. Further, if you focus on this vertically placed vessel, this is basically the bracket which has two horizontal plates and two vertical plates as gusset plates. So, this whole connection will be treated as bracket, and maximum compression load on each lug. Okay. So, as we have discussed that compression load will occur due to dead load as well as wind load towards leeward side. So, that we have considered for design purpose where both loads will be considered. So, maximum compression on each lug would be P, which is equal to 4 PW H minus HC by NC plus W max by N. So, let us see these parameters. P is the maximum compression load per lug. Pw is the total force due to wind load, which is given by this K1, K2, P1, H1 and D naught, where K1 is 0.7 for cylinder. Usually pressure vessels are of cylindrical shape, and K2 we have to take as 1, as period of vibration are usually very small, that is less than 0.5 seconds. So, when I consider tall vessels, their period of vibration is significantly higher than this. So, in that case K2 value would be taken as 2, but here vessel is of short height and therefore K2 will never exceed 0.5 seconds and therefore it is taken as 1. H is the height of vessel above the foundation and HC is the vessel clearance from foundation. So, basically H minus HC will be the height of vessel, and C is the diameter of anchor bolt circle, N is the number of lugs, and W max is the maximum weight of vessel with attachment. It means W max is the maximum dead load, N is the number of loads that we have already discussed, and when vessel is used for indoor purpose, we will not consider wind load, and then this factor would be neglected. Here you see, this is the schematic of vessel with bracket support, and here W max is there, P is there, wherever P will act, its arm is also given, and HC is basically height from the foundation and H is the total height, L is the height of column. Okay. Now, if you see, we have another parameter L and B and H. So, H is the distance between horizontal plates, L is total width of the horizontal plate, bottom plate, and B is basically the distance between gusset plates, and A is the length of horizontal plates. And we have seen the total load which is acting on each lug, and then we can discuss the stress in shell due to these brackets. Okay. So, that will be given as the axial stress due to reaction of lug. Now, first of all, you should understand this, that once I am having the vessel and below we have the support, this vessel will put compressive load to the support. Okay. And further, support will also react towards the shell, because it will try to react towards the shell, and because this vessel is acting downward, that support will act upward, but direction would be axial only or longitudinal only. So, in that case, axial stress due to reaction of the lug is given as sigma ZL, which is equal to 6 m by T square, and which is equal to beta cube P A R square by 2 1 minus mu square A into H. Okay, beta you can see from this expression, which is equal to 3 1 minus mu square divided by R square into T square power 1 by 4. These are the parameters used in this expression, and L whatever would be the parameter that we have already discussed through this schematic. So, once I know sigma ZL, that is the axial stress, I can study the, so once I know the axial stress, I can study the stresses generated due to internal or external pressure. So, once I am having these pressures, due to this we have the stress in longitudinal direction, and which is called, and which is given as sigma ZP, and sigma ZL is due to the lug. So, the design equation would be sigma ZL plus sigma ZB would be less than or equal to F. This F is basically allowable stress of support. Okay. And ZP you can find by this, where P is the design expression. Okay. Now, if you consider this particular equation, and if this condition is not satisfied, we have to take F as different material for support. And now we will discuss how to find out thickness of horizontal plate as well as gusset plates. So, thickness of horizontal plates, you can see from this schematic that horizontal plate is this, and the plate is fixed on the edges with the load P distributed over about half of the area of the plate. So, this P is basically distributed over half of the area of the plate, as you can see from this image, and then average pressure on the plate would be P by BL. So, what is that P by BL? P is the total load, and which is acting in almost half of the area, and therefore, we can consider B, which is space between the gusset plates, into this L. Okay. So, if I consider, I cannot see L over here, because L is basically the width of this plate outside. So, that is shown in this bracket clearly. So, B into L we have taken as the acting area, BAV will be equal to P by B into L. And maximum stress in a rectangular plate subjected to pressure PAV is given by this. F would be equal to 0.7 PAV L square by T square HP into B4 by L4 plus B4. So here THP is basically thickness of horizontal plate, all other parameters are usually known, and F is the allowable stress of horizontal plate material. In this way we calculate the thickness of horizontal plate. Now we focus on thickness of gusset plates. There are two web or gusset plates for each bracket as it is shown over here, and this is the expression to calculate thickness of gusset plate, where F is equal to 3p by Tg h square into A by cos theta. Theta is basically this angle. So Tg is gusset plate thickness and F is the allowable stress of gusset plate, and A you can see in this figure, which is this arm. So A is equal to C minus D naught by 2. So C is basically anchor bolt diameter, so that would be this diameter, okay, and this diameter minus D naught by 2, so that would be given as A. So in this way we can compute thickness of horizontal as well as vertical plate. Now we will discuss design of column on which these brackets rest. So design of column for lug support can be given by this equation. Here P by X by F equal to PA by Z plus PWL by 2 and Z divided by F, which is equal to or less than 1. Okay. So this P, if you consider this P is the total load on each lug that we have discussed earlier. X is the cross sectional area of the column. Okay. F is the allowable stress of column, and here P is P whatever we have discussed, that is the load on each lug. A is the arm that we have seen in the last slide, divided by Z. Z is basically the modulus of the structure. So this PA by Z, this is due to the eccentric load, because when P will act, it will have the eccentricity also considering A. So eccentric load will be considered by this expression, and this expression will be given due to wind load, as PW will be there. So what happens, this is the design equation where the extreme condition would be when it is equal to 1. Okay. So while equating this to 1, we will solve this equation and we will find value of X. Here X is the unknown parameter, which is the cross sectional area of column. So X is the cross sectional area of column, Z is the sectional modulus of column or structure, and L is the length of the column. Now what will happen over here, this I have equated to 1 and calculate value of X. So that X value would be minimum possible, because if X will have more value than the minimum, so this expression would be something like this, not equal to 1. I hope you are getting this. So whatever X I am getting from this expression, that would be the minimum possible cross sectional area of column. Okay. So as it is the minimum possible cross sectional area of the column, higher size of column may be chosen. Okay. So we have calculated minimum cross sectional area. We will refer the standard and see whatever area available above than this, that we can choose as the a right column for the bracket to rest. Okay. So from where I will get that standard? So as far as columns are concerned, we have definite shape for this, like I-beam, channel, etc. So if you consider this image, here we have this I-beam, where this is the structure of I-beam, and here we have the structure of channel. Okay. The bracket can support over here or can support over here, and this section will be connected to the foundation. Now once I am having this structure, I have to find the sectional area for this structure, and that we can found by this table. Here this table is given for I-beam column, and this is basically table C2 in Bhattacharya book. So you can refer table C2 in BC Bhattacharya book for I-beam. Now what happens? Let's say your minimum cross sectional area is coming as 20, okay, and here if you refer, here I have given sectional area for the structure. So as 20 centimeter square is the minimum value, I can choose 21, 25, okay. So in that case you can recommend ISLB 175 is the right column, or ISLB 200 as a right column, okay. You can choose further value, but that would be very large, okay. So you can use a higher value which is near to the minimum value. However, other parameter IXX, IYY and HB, all these value you can see from this standard. So here IXX, IYY and all these value you can see, which are also shown in a schematic which I have shown in last slide. So this is for I-beam. Now we have for channel. So here the table C3 is there in the same book, and again you can find out, again you can focus on sectional area for 20. You can see here I am having this okay, and here also I can have this okay. So you can refer ISLC 175 or value 200 like that, or ISMC 175 200 like that. So in that way you can choose the right column for bracket or lug support. Now we will see the design of bearing plate. Now what is bearing plate? For design of support, what we have discussed till now is the design of bracket, design of column. Now this column will attach to the foundation through bearing plate, okay. One plate is attached to the lower section of the column, and then that plate will be attached to the foundation through bolting or anchoring, etc. So bearing plate at the base of support is essential to increase the load bearing contact area with the foundation. The bearing plate which is welded to the bottom of the support of vessel must be secured, anchored to the concrete foundation by means of anchor bolt. So what is anchoring, what is anchor bolt, that we will discuss. So at present please bear with this, we will discuss that in upcoming slides. And it is embedded to the concrete foundation to prevent overturning from bending moments due to wind loads. So first we will see design of bearing plate, and then we will focus on whether anchoring will be required or not required, and what is the condition to check it. So let's start design of bearing plate. So thickness of bearing plate can be computed by this expression where TGP is equal to L root over 3 sigma C by F, and sigma C is maximum compressive stress between bearing plate and foundation, which is given by this expression where W max is the maximum possible load divided by pi DOS minus L into L plus M by this expression, okay. So here you see DOS is the outer diameter of bearing plate, that is DO outer diameter, usually we can consider this is outer diameter of shell plus 2L, okay. W max is the maximum weight of vessel, M is the maximum bending moment which is given by this expression, and L is the width of bearing plate. So when we have the column at the lower side of this, we have the bearing plate of width L, and then that bearing plate will be attached to the foundation. Further, if bearing plate thickness is greater than 20 mm, bearing plate is used along with gusset plates, okay. So here further we will use the gussets. So if you see this image here, basically this is the support, this is the column, and this is basically the bearing plate where this distance is given as L. So DOS you can DO you can consider as outer diameter of shell, because this will be aligned to shell, okay. And if you see in this image, this particular section is called as gusset plates. Okay. So, if TBP is greater than 20 mm, we need to consider the gusset plate and then we will consider thickness of bearing plate with gusset. So, TGP will come as 6 m maximum divided by F. So, here you should consider that initially we have calculated TBP, which is the bearing plate thickness, and if it is greater than 20 mm, again we are calculating thickness of bearing plate when gusset is used. So, TGP is not the thickness of gusset plate, this is the thickness of bearing plate only when I am using the gussets. So, M is the maximum of Mx or My, that is given in table 10.1 that I will show, but this table is given in book B.C. Bhattacharya, and B is the gusset spacing. So, once I know the gusset spacing, I can calculate number of gussets pi DOS by B. Okay, and this is the table where this is table 10.1. Okay, and here I am having L by B and Mx and My. So, whatever would be the ratio of L by B, accordingly you can find out Mx or My, and here in this expression you need to keep maximum values of these two, which is already mentioned over here. So, in this way you calculate the thickness of bearing plate. Now, next point we will consider where anchoring is required or not. For that purpose, minimum stress between bearing plate and concrete foundation should be computed using this expression where sigma minimum is equal to W minimum by A minus M by Z. Now, why I am considering the minimum stress? Because when I am considering stability of the vessel as well as support, the support will be most stable when it has the maximum load over this. Okay, it will not allow this to overturn. However, when I am having minimum load to this, it has more chances to overturn. Therefore, we are considering sigma minimum over here, which is equal to W minimum. Now, W minimum is what? Minimum weight of the vessel. Now, how I can calculate minimum weight of the vessel is weight of the shell and head, that at least this much weight will be there. So, that weight of shell plus weight of head we can consider as W minimum, that is divided by A and minus M divided by Z. This A and Z we can also see in the expression of sigma C. Okay. First, the denominator of first term will be A and denominator of second term would be Z. M we have already seen how to find this. So, in that case what happens when this weight would be minimum, and then this M is basically the bending moment. So, when this moment would be maximum, it has more chance to overturn. So, when sigma minimum would be less than equal to 0, bolts needs to be anchored. Okay. And if sigma minimum is greater than or equal to 0, whether it is anchored or not, that will be decided by stability factor J, which is given by this, where again I am using W minimum and capital M. So, if J less than 1.5, that support need to be anchored. Here skirt is written mistakenly, at this place support should come. So, when J is less than 1.5, support need to be anchored, and if J is greater than or equal to 1.5, support need not be anchored. Okay. So, let us see what is anchoring. Anchoring is basically when we bolt the material, we first let the bolt enter into the concrete foundation, and then we place the nut above to this. Okay. To make you understand the anchoring, we will focus on a particular figure, and that is this figure. Here if you see, here we have this concrete foundation, and in which the bolts are first entered. Okay. And then these bolts are placed in the concrete foundation, and this is basically the bearing plate, and then we will put the nuts. Okay. So, this is bolt and this is nut. So anchoring means some portion of the bolt is inserted in the concrete foundation and small amount of or a small part of that bolt is available at the top for entering bearing plate as well as to tight it through nut. Okay. So when it is anchored, it means it will not allow support to overturn. I hope I am clear. So here we have discussed design of bracket and lug support along with bearing plates. So that's all for now. Thank you.